All right, so I hope you guys remember from last time that we, we, we were basically computing the second order correction or second order contribution from the relative entropy. Okay, where the relative entropy, recall, is defined as the following. And maybe we can write this as that at epsilon equals 0. Okay, so that's what we're computing. No, it's okay. So I was just saying so far that from last time where we left off was we were computing the second order correction or second order contribution from this relative entropy. Okay, and that's the relative entropy is defined like this, and we want to calculate this particular second derivative. Recall from last time, rho epsilon is the density matrix on your subregion for the deformed state, and rho naught is the original state, which is the vacuum. Okay, so the way you compute this is you basically, well, first of all, the first derivative from here gives you two terms. Okay, just calculated the first derivative. This term here is actually 0. Well, you have to be a little bit careful in calculating the derivative of the log of a matrix. We'll do that a little bit carefully later, but roughly the point is that the derivative of the log is rho inverse times the derivative of the matrix. The rho here cancels with the rho inverse, and you get trace of the derivative of the matrix. Okay, because the density matrix is normalized, that's always 0. Okay, so this term is 0. You can do this more carefully by being careful about the derivative of the log, but you reach the same conclusion. Okay, good. So then now we can compute. You can forget about this term in taking this derivative, and what you get is well. So you see, this derivative can either hit that term or it can hit this term. If it hits this term, you get a second derivative of the density matrix. But that's going to get cancelled out by this guy here. Because at the end of the day, you're evaluating this at epsilon equals 0. The only place where this derivative can hit in this term here is on this guy. So that cancels, that second derivative piece cancels the second derivative piece coming from here. And so the only piece that contributes at the end of the day is and the whole thing evaluated at epsilon equals 0. Or I can maybe in some somewhat simpler notation write this as okay. I hope that's clear what that means. Good. So that's the expression for the relative entropy.
And that's not the same as delta 1 rho squared divided by rho?
Delta 1 rho. You mean from here?
Yeah.
No. So you have to be more careful with this. This is what I was referring to when I said that you have to be careful in taking the derivative of the log of a matrix. So let's do that more carefully now. In this term, it didn't really matter. The subtlety is not that important. Okay, so let's now let's compute this object here. Okay, the way you would want to compute that is so this is what you can think of this as
it's the thing when we compute a very routine Einstein's equations, right?
except that there's a log here, right?
Okay.
So the log is the thing that's, well, okay, so you'll see in a moment where that subtlety is. Okay, so far I hope,
Sorry. Yeah,
right. So far I hope you agree with this, this statement. Then let's rewrite this as that. And I'm not going to write this term anymore. It's just going to float around there. So just keep carrying it over to the next line. Okay, and this over here is basically, so rho naught, remember, is the exponential of the modular Hamiltonian, the original one. Okay, and I can roughly write this at the order that I'm working at first order. So at this order, I can write this as e to the rho inverse delta 1 rho. And again, this term. So far, so good. All right. So now you see where the subtlety is. The subtlety is that in multiplying these two, the original modular Hamiltonian need not commute with the first order variation of the density matrix. Okay. So you have to do Baker-Campbell-House stuff. It's not that hard. Okay. So as long as you're careful, what you get is you basically just do the standard Baker-Campbell-House stuff formula. And we only want to keep terms which are linear in this guy here. Okay? So what that gives is, a bunch of commutators. And now, well, again, sorry, I'm not writing this term, but you're always subtracting the original modular Hamiltonian. Okay, so then you can take the log. The log is the log of the exponential of this matrix is just minus k naught plus rho inverse delta 1 rho plus the series of commutators, which actually I can just combine all of these terms, and let me write that as a series. If you work out what the coefficients are, I'm sure you've seen this before. So there are n commutators in this term. And actually, you see this term that I was floating around here, that cancels the first term. Okay, so I'll just erase this guy here. Good, and these bn's are coefficients. They're Bernoulli numbers, but anyway, for our purposes, they're just these numbers, which okay, very good. So now what do we do with the series? Well, one sort of nice way to rewrite the series that we just got here is to use the fact that these coefficients, these Bernoulli numbers, have a nice integral representation. Okay, the integral representation is the following.
So in the case that k naught commuted with your
Yes.
rho naught delta rho,
Yeah, then you're fine.
I should see 1 over. Can you help me see that?
Yeah, so the n equals 0 term, right? The n equals 0 term is this guy. Forget all of the, okay, the n equals 0 term, forget everything else, just
the one with no commutator.
Yeah, no commutator.
Yes.
Okay.
That probably vanishes, right? Delta 1 or 2.
No, it's not, it doesn't vanish. It's just going to give you something. It's like trace of delta 1, rho inverse delta 1. It's what it is.
Trace of delta 1 rho will vanish, but here it's delta.
Correct.
Okay.
That's right. That's right. Okay, but here in general, well, you have this list of commutators. Okay, so now I'm going to use an integral representation for this Bn, and you'll see why that's useful. The integral representation is the following. Okay, just some formula. The I epsilon is just meant to avoid, like, basically you're avoiding the poles of this function in this contour. Okay, so now what you do is you take this integral representation and you plug it in here. Okay.
So could I ask, had this been something which had a Taylor series expansion?
What?
And
Which one?
replaced log rho by some function that had a power series expansion, then it would just be summing over all order orderings of the delta rho inside each term, right?
So power series in what?
In expanding around, yeah, I suppose this does. Sorry. Oh,
I mean,
sorry.
this thing is linear in the deformation parameter, if that's what you had in mind.
So suppose we had the function rho to the n.
Okay.
And
Oh, I see. Okay.
and I wanted to compute delta.
Sure.
It's what it would be with a number, except that you sum over all possible orderings of
Sure.
of delta.
Sure.
And then I was thinking anything that had a power series expansion in rho to the n, we could do the same thing.
Right.
That's a nice
But-
way to say it. Yeah.
But log is not.
But
does
you
not
could
have.
appro- you
That's
could
right.
approach it as n goes to 1.
That's right.
Probably
Yeah.
in the sense of this.
Effectively, what you're saying is equivalent to doing this computation in the Rennie version of the entanglement entropy. It's the Rennie version of the calculation. Here I'm just being sort of stupid and just trying to do the entanglement entropy calculation. Okay, very good. So hopefully you see that when I take this integral representation and plug it in here, the series exponentiates, right?
Yeah, I see. So now it becomes e to the power s edge k naught.
Right, exactly. Exactly. So it exponentiates in terms of the adjoint action of the modular Hamiltonian. So let me rewrite that expression somewhere. Is it okay if I erase? Like I'll write it here. Okay. So plug this thing in here, and what you get is okay. This is just it's the fact that the series exponentiates. Okay, very good. So now we have a somewhat useful formula for delta 1 of log rho. In particular, you see that these things appearing here, what they're doing is they're modular flowing your deformation. Okay, good. And that's going to play a crucial role in what we see next. Okay, I'm going to erase this. Very good. So now, in order to proceed, so now we have all the ingredients ready for the relative entropy. What we need to know is what this object is, right?
This
Yes.
kind of looks
Yes.
like the finger time representation of
Yeah.
quantum mechanics. Is there an interpretation of this that way? When we think of K0 as a Hamiltonian?
Yeah, sure. You can think of K0 as
That
some.
makes this probably more transparent, right? Why the Bernoulli number should kind of rearrange the series interval model.
Can you explain why it makes it more transparent?
In the sense, the integral representation you used was a mathematical formula,
Sure.
but finally it somehow became something physical, which is the modular flow of it.
Sure.
So that step did not have a physical, direct physical interpretation.
Sure. Okay. Yeah. Sure. Okay. I agree. But I mean, roughly the reason it. I mean, yeah. So this is the expression, which came from sort of BCH, and BCH has. So in this expression, it's kind of clear that if you expand this out, you're going to get a whole series of commutators, and those are precisely the commutators which came from BCH basically. But yeah, sure, I agree. Okay, good. So what I was saying was we need to know what this delta 1 of rho is. Yes.
So the assumption, not the assumption. So that second term, which you said was 0.
Yeah, this one.
Second line. So I should be able to see that if I now just
Sure.
trace this with rho naught.
Yeah,
And it's because rho naught is modular. It doesn't.
that's right. It commutes with the modular Hamiltonian. So in the trace, I can sort of cyclically permute. This thing cancels. The S integral goes away, and you get trace of delta rho. Okay. All right. Very good. Where am I?
I could try to do this heat kernel representation of log rho.
Sure.
So sort of like e to the power s rho ds by s integral
Yes.
from 0 to infinity.
Yeah.
And now do the
Sure.
Okay, and there we know that e to the power s rho, how to differentiate
Right, you can,
that.
right.
So it just s splits into some s prime
Right.
here
Right.
and delta rho there and e to the power. So that
Right.
looks a little more like what you have.
Yeah, I'm pretty sure you can derive the same formula using your method. You can also derive it using Shiraz's method, which is this replica trick calculation. So this formula has been derived in several ways. I find this the easiest to explain. So. Okay. Good. So now we need to know what delta 1 rho is. Okay. So from yesterday, I hope you remember that the density matrix. So we were working in states where the deformation is turned on by sort of turning on sources in the Euclidean path integral. Okay. So for the density matrix, so remember from last time, the density matrix looks like that Euclidean path integral with some sources turned on. So this is your region R. That's R complement. And you have some sources turned on in the Euclidean path integral. Okay, so with some you can put some whatever boundary conditions you want on this Euclidean path integral. And here phi, I'm just sort of vaguely denoting phi as the collective quantum field that you're integrating over in this Euclidean path integral. Okay, so what this picture here means is that for your deformed density matrix, the matrix elements of that density matrix the matrix elements of that density matrix can be computed using this path integral representation. Okay, that's what this picture means. Okay, so now what do I need to do? I need to compute the first order derivative of that density matrix. Well, I can expand. So what I mean by epsilon here is sort of these sources, right? When the sources are turned off, I get the vacuum density matrix. But when the sources are turned on, you get some deformation. So you expand in, so if you like, there's an epsilon sitting here. Okay? And so now you expand in epsilon. And in this calculation, note that I only need the first order change in the density matrix. Okay? This is proportional to delta 1. The other term is also proportional to delta 1. Good. So all I need to know is what's the first order correction. Well, the first order correction, it's matrix elements actually. That comes from just pulling down one power of the operator. I'm going to just Taylor expand inside the path integral. Okay, so far so good. All right, so and this is true for any matrix element of this density matrix. Okay, so now I can read off from this expression an operator statement. Okay, the operator statement is that maybe I write it here. The operator statement is that delta 1 rho is rho. It's the integral rho times this operator. Okay, is this expression clear? The clearest way to see this is to take this path integral and slice it along angular directions. Okay, slice this path integral in the angular direction. Okay, and then using the fact that this operator O, you can think of this operator O as basically in the Heisenberg representation as the following. Okay, so let me write it in the following way. I'll explain what I mean by this. Okay, so tau here is this angular coordinate, the angular Euclidean coordinate. That's tau. Okay, I'm calling that tau. In the yes.
I tau k0, is it?
No, there's no I. This is Euclidean space.
No, even so, k0 is Hermitian or not?
It is.
So there should be an I tau then, or not?
No, this is not real time evolution. This is Euclidean time evolution. So think about, for example, a density matrix is in this language e to the. Okay, just bear with me. It's roughly e to the minus 2 pi times k. So you go if you go all the way from 0 to 2 pi with this Euclidean evolution, then you end up generating the full density matrix. Okay, is that clear? You're right. If I had put an I here, that would generate real-time evolution.
Isn't k0 the generator of rotations around our?
It's exactly that.
So you're taking k to be I times j, is that right?
No, k is the modular Hamiltonian.
So the full evolution starting from phi minus to phi plus.
Yes.
I thought that should be e to the power I 2 pi times j. Right?
No, if that would be true if this were real time. In real time, you're right.
It's just the angle. Or what
Yeah, but this is the Euclidean angle.
I guess what's confusing us is that it's in Euclidean space that the boost becomes a rotation.
That's right. That's right.
And
So, for example,
I'm also a little confused about this. If we are right, that's the point.
Yeah, I mean the evolution operator through some angle theta should
Yeah.
be e to the power I theta j, isn't it? With j Hermitian.
Right. But I mean, I think you should think about this. So, for example, a thermal density matrix, right? The thermal density matrix is e to the minus beta h, but that generates the Euclidean path integral in Euclidean time with some.
So you're taking
Some
tau
length
to
to
be I theta. I see. You're taking tau to be I theta. Yeah, in that case,
But then,
yeah.
then tau would not be the angle.
Yeah,
The
yeah,
whole
yeah.
point is if
That's
tau
right.
is the angle, it should
Yeah, then it should be I 2 pi. That tau. Okay, I'm confused. If rho is a unitary evolution operator
Yes.
in your Hilbert space,
Yeah.
it should look like e to the power minus I 2 pi times.
But
k.
rho is not unitary.
Rho is well, you are representing the full path integral
Yes.
by that.
Yeah. So I think the easiest way to think about this is think of this as the thermal path integral. So in thermal field theory, you can represent your state, your thermal ensemble by a path integral.
Yeah, e to the power minus beta a.
Right. I'm not sure how to draw it, but there you go. So that's your thermal direction. Let me call that tau as well. And then e to the minus, if you go all the way from 0 to 2 pi, then that gives you e to the minus beta h, right? This is the same thing. Except now my spatial direction is not a line, but it's this half space. That's all it is. Okay. All right. So yeah, just think of this as the thermal path integral. Okay. Good. Very good. So if you buy that, then using this Heisenberg representation, you see that this operator statement is equivalent to this path integral statement. Okay. Why is that? Because in this operator statement, what you have is first you have e to the minus tau k naught. So suppose your operator is inserted somewhere here. Then this piece of this operator first creates the path integral up to this point. Then you insert this operator. And then this piece combined with the rho naught here generates the remaining path integral. Okay.
But what is the statement exactly?
The statement is that delta 1 of rho from this path integral, you can read off what delta 1 of rho should be. So this is a path integral way to compute delta 1 of rho, or matrix elements of delta 1 of rho. From that, you can just get this operator statement. Okay? So that's the result I'm claiming for delta 1 of rho. Yeah, yeah.
Stupid about
No, no, go ahead.
about why that O is not inserted in the middle of rho. Suppose we just take quantum mechanics.
Yes?
Got some density matrix of T1 and T2.
Yeah.
And you put an operator in the middle. You do the path integral.
Yeah.
Then you put the matrix elements. Then you do the path integral.
Exactly. That's exactly what this is doing.
But why is that the same as what you wrote there? I mean,
Yeah, yeah. So, okay, let me write it more better. So forget.
Okay. No. Why?
Yeah, yeah. For the integral is not important, right? Okay, let me write this.
Yeah, it's just the integral.
This is not important.
Yes, forget it.
So this, okay, so this piece here is e to the minus 2 pi k.
Right.
Sure. I'm actually sort of mixing up notation a little bit. Before I was not writing this 2 pi, but it's better to write the 2 pi because it says that the density matrix is the full thing. So you go from 0 to 2 pi.
Fine.
Okay, so this is like the temperature. Okay, so now let me use this Heisenberg representation. This is saying that. So now if I combine these two terms, what you see is that this whole thing combines into.
Right.
Okay, so now this should be clear in this way, right? So as you exactly said, this piece creates the path integral up to here.
Yes.
Then you insert this operator,
Yes.
and then you do the remaining path integral.
Yes, but why is that same as rho naught times O? Rho naught.
But that's exactly what I started from this expression.
I see.
Because he's writing it in terms of theta of x in terms of theta of O.
Yes. Yeah, this operator, I'm writing it in the Heisenberg representation.
Okay, thank you.
Okay, so yes?
The operator that has to be
It's whatever you want. I mean, for our purposes, we can insert the stress tensor because we are interested in like the second order Einstein's equations in the bulk. But for now, let's take it to be a scalar operator. I'll do the calculation with a scalar operator, and then everything works the same way for stress.
Somehow it has to be related to this epsilon change that you've done.
Yes. That's right. So the epsilon. So remember the way the way the state is being put out is I'm turning on a source for this operator in the Euclidean path integral. Okay, so you can think of this epsilon as being.
This delta psi that you had is created by that operator.
Right. Exactly. That's right. In this Euclidean path integral sense. Okay, very good. So now we have everything we need. We know what delta 2 of the relative entropy is. We know what delta 1 of rho is. We know this object. So let's put all this together. And so then we can write a nice formula for the relative entropy, the second order relative entropy. Okay, so what is it? So the second order relative entropy. Okay, I have to say one more thing, but okay, let me write this formula first. Okay, all I've done is I think I erased this formula, but you'll remember hopefully that there was a formula for delta 1 of log rho involving this modular flow and this and that. I've just plugged that into this formula for the relative entropy. Good. So now we know exactly what this object rho inverse delta rho is from this thing that we just derived. Rho inverse delta rho is just the integral of a local operator. Okay? But yes.
No issue with commuting the integral across the trace.
Should I be what?
So the
What should I do?
integral inside the
Yes?
It was a delta 1 log rho.
Yeah, okay. I've commuted the integral. What? Yeah, I've commuted the integral. Yeah, you can justify that by using the spectral representation of the trace, if you like. It's two sums are commuting across each other. Yeah. Yeah. So at this point, if you stare at this expression, you should be a little bit worried. The reason you should be a little bit worried is because I'm telling you that this object is the integral of some local operator, both of them. But for this trace to make sense, these should appear in the time-ordered combination. Okay. If the operators appear in a time-ordered combination, then this trace sort of is meaningful, and you can rewrite it as the two-point function, the Euclidean two-point function. Okay. A priori, that's not obvious. By the way, what I mean by time ordering is in this angular sense. Okay.
Why is that? I don't see.
Sorry, what's?
I don't see why it has to be.
Right.
Time ordering argument.
Yeah. So the point is, so let's take one particular combination. So this rho naught here is e to the minus 2 pi k, and then there are two operators. Okay, for argument's sake, just forget about the modular flow. That's not super important here in this argument. So there's one operator coming from here, one operator coming from here. Okay. And I'm just writing the angular location of this operator. The one at tau A, the other at tau B. Let me write it this way. Okay, so if the configuration is as drawn, then you're good because everything is time ordered. Okay. But if it's not, if tau A is smaller than tau B, then what's going to happen in an intermediate step here is you're going to get e to the some positive number times k. Right. So if you write this out in more detail, what this is sorry, I'm going. Is this clear? This is just the Heisenberg representations of these operators. Okay, so if tau A is greater than tau B, then everything is fine. But if tau A is less than tau B, then here this term has e to the something positive times k. Okay, that's bad because that's not a bounded operator. Because k can have arbitrarily large energies that can give you a divergence. So in Euclidean space, non-time ordered things are always bad, and this is the reason. Okay.
Where does the time appear in delta rho?
Yes, so delta rho is this, and the time is basically the tau coordinate inside x.
But the integral is only over the spatial.
No, the integral is over everything. It's a d-dimensional. X is like tau and everything else. Yeah.
Because of the integrals, there is no.
That's
no
right.
Particular ordering.
That's right. Right. So you might be a little bit worried about that. Okay, but that's not a problem. The reason that's not a problem is, as I said, when tau A is greater than tau B, you're good. Everything is fine. When tau A is less than tau B, actually what you can do is you can move this contour, this S integral inside your spatial integrals, and then shift your contour by 2 pi to reverse the ordering. Okay, so let's. This is your S plane. Your original contour is this one along the real line. The sinh squared has some poles. They're just below the. So let's say this is 2 pi. The other pole is sitting up here, and so on. There is a series of poles. What you can do is you shift this contour up here. Okay, you can do that because there are no non-analytic. There's nothing non-analytic happening here. So you can do that, and once you shift this contour up here, you can check that the time ordering is fixed, because shifting S by 2 pi shifts these operators by 2 pi, and that's 2 pi I, and so that precisely has the effect of fixing the right time ordering. Okay? The only price you have to pay is that you have to take this integral inside these integrals. And so now let me write down a better formula for you, which makes it clear that there are no time ordering issues in this relative entropy. So the better formula is the following. These are a whole bunch of integrals, and then you have the trace of rho naught time ordered okay. So the only thing I did is I took the contour integral inside, and then I played this game of shifting the contour around depending on the sign of tau a minus tau b. So that's what's giving me this extra piece here.
What happened to the e to the ISK?
Ah, sorry, my bad. That's sitting here.
And you don't have to worry about the positivity of that when S gets
No, because that's an expert. That's e to the I times something. That's oscillating.
ISK, but then at some point you're shifting the contour.
Oh yes. So you get that's exactly the point. So those two e to the 2 pi k's that you get precisely have the effect of shifting reversing the ordering. Okay, so my claim is that this is a better formula. It just makes it more manifest that there are no divergences. Okay, but now you're in business, because what this object is, this time ordered trace, is the 2-point function. It's the Euclidean 2-point function. Okay, so now I can just happily rewrite this as the Euclidean 2-point function. Okay, Euclidean. Good. And furthermore, if you needn't be worried about these modular flows, because these modular flows in the present case, where we are working around ball-shaped regions, these are just ordinary boosts. Okay. So what this is doing is it's just boosting this operator in real time.
Boosting the operator
In real time. In real boost, that's right. Boost parameter time. Okay, very good. Right. So now we have so far we have a formula for the second order relative entropy. So now I have to show you that this formula exactly matches with what you would expect from gravity. Okay. For that I have to play a trick. Well, before that, actually, it's useful to rewrite this formula okay. So you can rewrite Minkowski space in terms of coordinates, which make it look like S1 times hyperbolic space. Okay, Minkowski space is conformally equivalent to this. Or sorry, Euclidean flat space is conformally equivalent to S1 times HD minus 1, conformally. And so you can rewrite this expression in those coordinates. Okay, it's just convenient to do that. And all that does is basically this S1 is parametrized by tau. Okay, what I was calling tau before, it's this angle direction, and the hyperbolic space is basically the remaining half space coordinates. All right. So I just wanted to mention that. Can you say that again? What's the
slicing of Euclidean space that gives that conformal map?
Yeah.
Can you remind us of that?
Oh, sure. Yeah. So it's extremely easy to explain this for half space cuts. So suppose that this is x1. This is your Euclidean. Well, let me call this x0. It's the Euclidean, what you would usually call Euclidean time. So then what you do, and remember what I was calling tau is this angle. Yeah, you divide by r. You divide by r.
dr square plus r square d theta square.
So yeah, is that clear?
Theta square is that thing, and then divide by r.
d theta square is usually
Okay.
s.
Yeah, right. So the metric is
No,
basic.
it's literally theta. You need two planes here.
Oh,
Anyway,
theta square is the
yeah.
So the metric of flat Euclidean space is this one, where these xi's are the transverse coordinates, and then you divide by r square. That's the conformal factor. Okay. And you can do a more sophisticated version of this for ball-shaped regions, because ball-shaped regions are conformally equivalent to half spaces.
You split it into a two plane and the remaining.
That's right. That's right.
And then
That for half spaces, that's the natural thing to do. Yeah. Okay, so what I'm going to do from now on is I'm going to use the notation that x is basically tau. I should have said that these a and b subscripts are just sort of differentiating the two operators. I suppose that's obvious. But I'm just going to use this notation from now on.
So could you remind us on the gravity side, this is, we were trying to prove that this was equal to some expression.
Yes.
Could you remind us what
Yeah.
that was?
So the claim is that this is equal to the integral of the following expression. It's this symplectic flux.
Yesterday's left-hand side.
Yes, that was yesterday's left-hand side. Yeah, and this is integrated over the bulk entanglement wedge.
Just read the last part. Integrated about.
The bulk entanglement wedge. So, okay, so in pictures, this is your boundary region, this is the boundary domain of dependence, there is a bulk in this slice here. Yeah, that's where it's integrated.
So that would be a d plus 1.
It's D because it's codimension 1 in the bulk.
Yeah, the Lewis-Achanidi is codimension 2.
That's right.
This fills it in.
That's right. That's right. Good, good. So yeah, I was just saying that I'm going to use the notation that these boundary coordinates can be coordinatized in terms of this S1, which is the angle, the thermal direction, if you like, and everything else, which is basically these coordinates on hyperbolic space. Okay, the capital Y's are hyperbolic space coordinates.
So you're taking the O's to be basically stress tensor?
You can. For now, I'm going to just use scalar operators. I'm going to run through the whole argument with scalar operators. And
But then
yeah.
You should include matter fields or not.
Sorry, yeah, okay, you're right. So this, what you're going to find is that when I repeat this, well, if you repeat the same argument with stress tensors, then you end up generating this object. Yeah, that's what I meant.
What do we get if we use scalar operators?
You get a similar expression, but where the symplectic flux is the symplectic flux of that scalar in the bulk, and then this is delta phi. Which is why I'm going to run this argument in the scalar case, because the argument is exactly the same. Okay. Good. So now comes the trick. Now comes the trick.
So
yes.
there were these lambdas, which should be the boundary values of the
That's right.
fields and so on.
It's the
That
boundary value of the source. The source.
expression would go into this.
It will go into this expression. Yes. Yeah. You'll see how that.
But it'll go into it just by producing the bulk field.
Exactly. That's exactly how it enters. Okay. Good. So let's start with this 2-point function. Ignore this for now. That's where we want to go. Just look at this 2-point function. Okay. By using this time translation invariance in the angle direction, I can put all of the sort of Euclidean angular dependence on one of the operators and keep the other operator in real time. From now on, whenever I say time, I just mean this boost time, not the usual time. Okay. So then the 2-point function that we are interested in is of this form. Okay. The other piece of notation is that when I write tau, I always mean Euclidean time, and then when I write s, I always mean real time. Okay, so that's something that you will have to sort of just keep in mind, because I don't want to keep writing i's all over again.
So just to understand,
Yeah.
you said this, but xa is tau a, y a, so
Yeah.
tau is the coordinate, angular coordinate.
Right.
And okay, then
These are the coordinates on hyperbolic space. So remember I said that Euclidean space can be written as conformally equivalent to S1 times hyperbolic space. This is the S1 coordinate, and this is the hyperbolic space coordinate. I'm just denoting it as.
okay, no, sure, but then when you write the two operators, one has argument tau and the other
Yes.
has argument s.
Yes.
You mean one has a real and the other has an
Yes.
imaginary?
So what I did was in particular this has some tau and this has some tau b.
So you translated.
Yeah, using time translation invariance, I can put that on the other side. And then this other operator only has this s. Okay. So really this tau is good. So now the claim is the following. This two-point function can be written in a sort of gravitational way in the following way. So this is my boundary CFT. Imagine that there is some fictitious ADR spacetime, okay, on the boundary of which the CFT lives. Okay. Now this is my boundary subregion R, and this is now real time. Okay, so this is the domain of dependence. But imagine that this slice is sitting at some cutoff value in this bulk spacetime. So let's imagine that this the slice is sitting at some cutoff value. So let me call it z bulk going to 0. Okay, so this z is the bulk Poincare coordinate. It's sitting at some slice at asymptotic infinity. Okay. Then the claim is that you can rewrite this expression in the following sort of gravitational way. At this zb going to 0. And I'll explain what all of these things mean in a second. Okay, that's a pretty complicated formula, so let me unpack that a little bit. First of all, this omega is the same thing as what it meant yesterday. It's the symplectic form. Okay, so if you're working with scalar operators, then this is the symplectic form of scalar operators. So more explicitly, this object omega is essentially like square root of minus g minus gamma. The normal vector okay, and this normal vector is basically the radial vector in the bulk. Okay, good. So now what are these things that I've plugged into? So this is omega of. Remember that omega takes in 2 entries. So there are 2 entries here that I've written out. The first entry is the k's are bulk to boundary propagators. Okay, so the first entry is the Euclidean bulk to boundary propagator, where the boundary source point is this guy. It's the entry of the first operator, and the bulk point has been analytically continued to this region here. So this point here, this is the bulk point. I've written it again in bulk coordinates, which are sort of adapted to this S1 times hyperbolic space picture. You can think of this radial, so there's corresponding to this region, there's some bulk, and so this r coordinate is sort of the radial coordinate in this bulk and bulk direction. Okay, it's not the usual r coordinate that we mean in ADS. It's not 1 over z. It's this coordinate which, when r goes to infinity, you are at the boundary, and as r goes to 1, you sort of hit the horizon of this hyperbolic black hole.
And sorry, is it that actually, if you had allowed the integral outside the causal development, it would have vanished anyways, so you can restrict it? Usually you would have just said to compute the two-point function,
Right.
just do the entire bulk integral.
Sure. I think you're right. I think.
Just vanishes.
Right. So I think if I take this point outside the causal domain, then I think the integral probably vanishes, but I'm not completely sure on that. Yeah. It must. I think it must.
Otherwise this
That's right. In particular, I think it vanishes because, okay, I didn't say what KR is, but KR is the retarded bulk to boundary propagator. So one is the Euclidean. So the thing is, if I put both Euclidean propagators in here, then this quantity should probably vanish because omega has to be antisymmetric. Right? Omega is antisymmetric and it's 2 entries. So I better put 2 different things. And the things are, well, one is the Euclidean bulk to boundary propagator. The other is the retarded bulk to boundary propagator. Okay?
So in terms of 2-point functions, typically would be represented by some Witten diagram
Yes.
and so on.
Yeah.
So this is some geodesic approximation to the Witten diagram where the Lycon, etc. structure is showing up? Or
No, this is not the geodesic approximation. Well, you can think of this as.
otherwise they will
yeah.
be all over. No? I mean, as
No, so this is the leading piece in the 2-point function. If you just do the sort of take the linearized fields in the bulk and calculate the first contribution to the 2-point function by just doing the bulk to boundary propagator.
Is it the same as saying, for at least for scalars, is it the same as saying you are calculating the inner product that will come from prime dot inclusive in the bulk?
Yeah.
These are the bulk to boundary propagators, which are the wave functions.
Yeah.
You are just calculating prime dot and inner product for the leading functions.
Essentially. But there is a little bit of complication because these wave functions are different. One is retarded, one is Euclidean. But
Yeah,
up to that,
because yes, of one of them is some lot in the analytic confusion. I'm not sure of, but
yeah, roughly this is like the symplectic product. I agree.
But at this point, you're not using some information about the equations in motion in the bulk.
Yeah, so I am using the fact that KE and KR satisfy the linearized
But
equations.
are we trying to derive?
Linearized equations.
These are the linear.
Yeah.
Just the linear.
And we're trying to derive a second.
Right. That's right.
Once you fold it into lambdas,
Yeah.
these become the first
Bulk
order
field.
variations.
These are going to become the first order bulk fields. The reason why this is true, by the way, is that the 2-point function in the CFT is universal. Okay, so it's some conformal structure, and it's fixed. Okay, so if you do this calculation using ADS, then you're guaranteed to hit that structure, but you're going to get some overall coefficient. That coefficient may not match. Okay, so up to the
If ADS CFT were true, this would have to be true, and it's easy to check explicitly.
yeah, you can check explicitly. I mean, these are functions, right? These are not mysterious objects. There are some functions, you plug them in, you get something, and that's the 2-point function. Okay?
What was D
D of R is the domain of dependence of R. So R is my boundary subregion, and D of R is it's the domain of dependence. It's this thing. It's this diamond on this slice in the boundary. Okay. All right. So right. So so what is the? I mean, do you want me to go through the derivation? If you guys want, I can derive this expression for you. Is that something people are interested in? Not okay. So okay, technicality. Okay,
I
fine.
just want to understand the, sorry.
Yeah.
So this RB, SB, YB, that's a bulk point?
That's the bulk point. So,
Where is this bulk point? I mean,
Yeah.
iterating over the boundary, right?
right. So it's
Bulk point is located?
Right. So right now this integral is being done on a bulk slice, which is sitting at asymptotic infinity. So think of this as your EDS spacetime. The slice is sitting at asymptotic infinity, and this bulk point lies on the slice. But it's restricted to this domain of dependence within that slice. Okay. No. So okay. So good. So ZB just tells you which slice you're on. RB is essentially at asymptotic infinity. It's essentially the same as 1 over ZB. R is 1 over Z, but if you move into the bulk, then RB is not the same. RB is this sort of black hole radial coordinate. So it's only a coordinate which makes sense inside this bulk entanglement wedge, or the domain of dependence of the bulk entanglement wedge. It's a thing which becomes 1 when you go close to the horizon of this black hole. RB is not being integrated over. Yeah, all that's being integrated over is this domain of dependence.
But finally, you take ZB to go to 0, right? To get the 2-point function.
Right. Yeah, you have to take that to 0.
This geometry is kind of complex geometry in the sense you're keeping real and imaginary time both.
Yes. Yes. So I mean, you can think of it that way, but the way I would say that is it's just analytic continuations. These are some propagators. You just you compute the analytic continuations. Okay. Very good. So that's what it is. All right. So now having I hope more or less convinced you that this is true. Well, I haven't convinced you, but I told you that this is true.
So if M was like the time vector, then this symplectic form is something that I would expect, which is d phi wedge d phi dot.
Yeah. So this is like a radial version of that. Imagine that the radial direction is time.
This is the symplectic.
Yeah. Okay, so this is just some identity at this stage. All right, so now comes the.
Everyone else seems to have got it. I still find this formula hard to.
Or maybe I should just go through the derivation. Is that or not? No.
Will
Okay.
it take a long time?
No, probably not. Okay, so let me just do it. Let me just do it. Maybe that's useful. All right. So the
Yes, Euclidean and retarded and so on.
right. So the point is very simple. You can take. So let me just sort of schematically denote each of these entries, or sure each of these entries as delta I of phi. Because I told you that these guys satisfy the linearized equations of motion at asymptotic infinity, they satisfy a particular fall-off, right? Yeah. Okay, this is true for both of these objects. Okay, so what are these? So okay, first of all, the first thing to say is that you can take this and you can plug it into the symplectic form. Okay, the reason I'm allowed to do that is remember that the symplectic form is being evaluated on this boundary, this slice at asymptotic infinity, right? So I can always, so for that reason I'm only using these asymptotic formulas. Okay, so if you do that, then what you find is let me define this object capital W, which is just the integral over the domain of dependence of little omega. And what you find is that this object is basically up to some overall constant. It's the integral of a1 b2 minus a2 b1. Okay, this should not be surprising. It's just saying that these two coefficients are just the conjugate moment. They're conjugate to each other. Okay, and so then now I don't want to erase this. But okay, so let's see what these a1 and b1 and a2 and b2 are for these two objects. Okay, for the Euclidean guy, for the Euclidean propagator, You see A1 has to be 0. The reason A1 is 0 is because A1 is essentially the source, right, the boundary source. The Euclidean propagator is being sourced at some Euclidean point in the boundary, but the bulk point is Lorentzian. So that delta function can never click. Okay, so A1 is 0. B1 is the Euclidean two-point function. Okay, with essentially S. Is a Euclidean two-point function. And for the retarded propagator, A1 is a delta function. Okay, it's a delta function because now both of these points are in Lorentzian time.
So do I understand what you're going to do is to use, as you said, the boundary forms of these things,
Yes.
and then just get an expression which you independently know is the propagator of the field theory.
Or the 2-point function.
The two-point function. Yeah.
It's not coming through the logic of ADS-CFT.
No.
Okay, now I get it.
It's the two-point function which is universal. So it's some structure, right? It's some
It's
geometry.
some simple identity.
Right. It's a simple.
Okay, I better understand now.
Okay.
No, what was confusing me was how do you use the ADS-CFT rules to get this?
Then no, not
Wait, I said something
Wait,
wrong.
so how do the lambdas get into this game?
not so far. I'm just looking at this two-point function.
At the moment, this is, if I could paraphrase,
Yeah.
this is just a simple manipulation because k's are so simple at the boundary.
Yes.
So it looks very complicated, but it's evaluated near the boundary.
Yes.
So it's just some very simple.
Yes.
It's a complicated way of saying something simple.
Exactly.
And,
That's right.
And the complication will be useful the next time.
Exactly. These are just some functions. You can think of these as functions if you want.
With this also, I thought that you were going to take the A's to be the lambdas, or not?
A's. Oh no.
No?
Okay. So
Then I'm getting it completely wrong.
good. So let me try to explain that.
Yeah.
So the lambdas are sitting here, right?
Yeah.
So let them be there. Just look at this two-point function.
Right.
Okay. I'm saying that this formula is just true of this two-point function.
Yes.
Okay.
Yeah.
And in this the way I'm computing this two-point function is I'm plugging in.
Oh, I'm sorry. So that's only about the 2-point function.
Exactly.
itself. Okay, right.
Yeah. Okay. That's all. So these sources and waves that I'm talking about are just the things which are corresponding to the asymptotic behaviors of these propagators. That's all. I'm not talking about the source, those sources right now.
And if you were to complete this derivative, it would just be algebra.
It'll just sort of multiply.
Okay, so I feel we could omit the.
Okay, good. Okay,
You
good.
can play same type of games for more interesting states. Like monopile double state backed by some other operator. You can have the similar interpretations that bulk to boundary propagators are giving more functions, things like that.
Yeah.
In this case, it is totally trivial.
The thing that makes it sort of trivial is that you're evaluating it very near infinity.
Right.
Yes.
For now. For
Right.
now. Yeah. For now. Yeah.
But it would be true not evaluated at infinity.
Yes. Yes. As long as you keep sort of this boundary, this light cone boundary fixed, and say I take this expression and I push it into the bulk. Okay. Because the symplectic flux is conserved, this expression is the same. It doesn't change.
Once
Okay.
you write it in the general form with KE and KR,
Yes.
that would be extendable too.
That's right. So first of all, because these things satisfy the linearized equations of motion, as long as that's true, the symplectic flux is conserved. I can just sort of push it in the bulk and evaluate it wherever I want.
Are you saying that using the symplectic flux idea, I can push all calculations of Witten diagrams towards the boundary? Is that what you're saying?
So what I'm saying right now is that at least the two-point function.
For 2-point.
Yes. For the two-point function, I can rewrite this Witten diagram calculation, the first Witten diagram that you get, just the
Yeah.
bulk to boundary property. I can rewrite that calculation as an integral deep in the bulk using the symplectic flux idea. Yeah.
Wow.
But
Okay.
in more interesting cases, you might not be able to do this. In the sense that you might not be able to evaluate it just going near the boundary.
So why is it not the generically interesting thing? What's missing here?
Let's say if you have 4-point functions and you try
Right,
to do similar
right.
things.
It's not clear whether you can always do this at higher and higher point functions.
I see. So I see. 4-point or even 3-point. Yeah. Is it?
Even 2-point in a non-trivial state, it's like vacuum you're working. I can play because I have 4 points.
I think 2 point.
can do-
I think 2-point function is more generally true.
You just have to find a bulk boundary propagator
Right.
around that background.
Right.
Yeah, so around that background, and then you might have contributions from other places depending on what kind of background that is. What I'm saying is the 4-point function is same as 2-point function. Once you take the other two operators stating the state, if it is that kind of configuration.
Yeah, it's not true in general. This is sort of an earlier version of this, which we've all seen, is that sometimes you can compute transport coefficients at the horizon, like viscosity or something. Again, you compute it at the boundary because something comes out.
Right.
When this
Yeah,
happens first,
I think this is somewhat similar to what you're finding. Yeah. Okay.
It's more complicated with two Euclidean retarded, but
Right. A little bit more involved. Yeah. Okay. So
So
yes.
general conclusion is, in general, you might need to worry about the inside unless you have some identity, right?
Okay, good. So now the trick, once you've believed this expression, the trick is the following. So this is your boundary, and this is sort of the Ryuta-Kenagi surface, or I guess I called it R tilde yesterday, and that's the domain of dependence of the Ryuta-Kenagi surface. Okay, the symplectic flux is being evaluated out here at asymptotic infinity. But as we were just saying, it's a symplectic flux, so I can push it, okay? And I can push it all the way to the horizon of this black hole. Okay, so that's what I'm going to do. I'm going to evaluate the symplectic flux right at this horizon here. So far, so good? Okay. Once you do that, now actually what happens is that the merit of doing that is that the S integral, which involves this modular flow and so on, simplifies greatly. Okay, that's why you want to do this. So let's see how that happens.
Something fun, is something particular I'm thinking at the boundary of this?
Which boundary are you talking? This one?
That one, yes.
So that's like S going to plus and minus infinity. I don't think that's singular because then this, at least at the level of the relative entropy, the sinh function basically exponentially decays. And so I think it's regular. So also the 2-point function exponentially decays at large S. So
X was what, please?
S is this boost time.
Edge of the ball, right?
It's no. So from the boundary point of view, so let me take this boundary domain of dependence and redraw that. So this is just in the boundary I'm drawing now. S is this time, this boost time.
Okay, so it's the light cone of the ball. S goes to infinity?
Yeah. That's right.
And
So well, okay. It depends on how you take the limit. If you fix the spatial location and take S to infinity, then you reach here or here. If you take the light cone limit, then you can take the light cone limit if you want, but that's when you hit the light cone.
I mean, I was confused. We normally evaluate symplectic fluxes over the whole space.
Yeah.
Here you're doing it over some part of it.
Right.
And I was wondering whether there's some boundary choice.
Okay, that's a good question. I don't immediately know what goes wrong, but I think outside of that space it vanishes because the retarded propagator vanishes.
Yeah,
As
so some
Sandeep
causal
was.
distance,
Yeah.
And this diagram, let me just make sure, this isn't the boundary theory. Where is this diagram?
Which diagram? This one?
That side.
This one.
Yeah.
This is the bulk theory now. So this is my boundary.
But
This is the bulk radial direction.
yeah, but now that left-hand side diagram you had, no, just below that.
This one. This one is a boundary
This
diagram.
one was in the boundary.
Yeah. This is this
And
domain of
so
dependence.
So that null ray and the limits of the null ray on the right, sorry, just to understand, that's the horizon in the bulk.
This one? Yeah.
Yeah.
This is the horizon in the
In
bulk.
the bulk,
Yeah.
right? And still a bit confused. That is supposed to, I mean, the S parameter there is on the left side, right?
Yes.
So just making sure.
That's right,
I mean,
that's
what
right.
is the,
So this is the S parameter. It's on the boundary.
I mean, just making sure I understand.
Yep,
because
yep.
Going very far along, the horizon is different from S.
That's right. This is S. This is S.
The thing
This is
was-
S.
Right. So this is like, there's a diamond on the boundary.
Ha,
Yep.
So this wedge that you were integrating as you took the z goes to 0 limit
ha, ha.
was a wedge with the edges on the diamond of the boundary.
Right.
And now you're going to blow this surface up so that it goes into the
Right.
But you'll have to keep the boundary of that surface
Fixed.
fixed.
Yeah, that's right.
So it's not like you're uniformly going to large z. I mean,
Right.
small z.
Right.
Yeah, part of it has to
Always.
always be.
Yeah.
In this very particular
That's what you were
That's
worried
what I was
about,
worried
where it
about.
was hooked
Yeah,
in.
yeah.
I see.
That's right. I mean, from black hole,
With you.
in black hole terminology, you're pushing to the horizon of the black hole.
Yeah.
You're
that's all.
pushing towards the horizon, but
Right.
part of it always comes.
In this case, the horizon comes and
Comes back.
hits you at the
Okay.
boundary. So.
Good. All right. Go ahead.
Yeah, okay, good. Very good. So now what I was saying was that having written this expression in this form, you can actually do the S integral. Okay? The way to think about that is the following. Well, first of all of the S dependence in this expression only sits inside this retarded propagator. Okay? So let me just do the S integral over this retarded propagator. There's some I epsilon, which I'm not going to worry too much about. Okay, that's where all of the S dependence in this expression is sitting. Good. Now, what I just told you is I want to take this bulk point. So this is the bulk point. Remember,
It's very embarrassing. But what is it? This integral in omega, what is being integrated?
this integral.
Yes.
This is the bulk point which is being integrated.
So-
Right. So this is sorry.
So I thought there were insertion points.
Yeah, good. So the RB is this bulk radial coordinate that's fixed to go to infinity because
Yes.
you're right. So if you like, I can rewrite this as RB going to infinity.
Okay.
That's fixed, and then you're integrating over these things.
Why B and why A were not the insertion points of the boundary?
They are.
Then how can they be?
They're not. So I'm fixed. These things are not being integrated over.
Oh, capital B and little b are different.
Oh yes. I'm sorry. So
Okay.
this is the bulk. This is the bulk point.
Yeah.
Bulk point. Okay, and these things are the source points, the boundary
Yeah,
points,
yeah.
and they're not being integrated.
Yeah.
There is further integration over those later.
Later. I'm not doing that right now. That's later. Okay.
Thank you.
Yeah, sure. Okay, so good. So having said that, so now what's going to happen is we're going to instead. Yes. Go ahead.
Because I was thinking the whole integral will localize to boundary. I mean, if you're computing del phi square and you're allowed to use the equation of motion, you will come to phi del phi ultimately. And that's what I thought was happening with some complications about the propagators. Now,
Yeah.
if you have a bulk integral in addition,
No. There's no bulk integral.
then what is
I said that. So RB is fixed, right?
YB is what now? YB?
Right. So good.
Sorry.
No.
It's just on the hyperbolic plane. So this is actually a point in the boundary, right?
It's a field theory.
It's a field theory coordinate,
right?
but
Okay, yeah.
Yeah.
All right. I keep getting confused. I somehow thought suddenly you said it was in the bulk.
it's effectively a bulk point because remember that I'm thinking of this field theory as living as a slice at asymptotic infinity. So that's why I was calling it a bulk point.
Well,
That's-
this is a field theory coordinate direction.
It's the part of the bulk that's in the field theory.
Right. That's right.
Yeah.
Yeah, but eventually he's going to take RB to go to
Yeah,
infinity. So
yeah.
morally speaking.
Yeah.
Right. But
I understand.
yeah.
Okay, fine, go ahead.
all right, very good.
Certainly
But
I
now what I'm going to do is I'm going to take RB to 1. So what I'm telling you
Yeah, I
is that
understand, and therefore it goes in the bulk.
Right.
Fine, I
okay.
understand that
So
you-
okay, good. So now let's take RB to 1.
Go ahead.
So then your so
Isn't it like the codimension one time slice on which you will do the inner product? So I am thinking
codimension
about
one,
this-
you mean? Yeah, codimension
Yeah,
one.
codimension one because this RB is fixed.
Yeah.
Roughly, like usual ways of doing it will be like let's say fixed time slice.
Yeah.
You take the bulk to boundary propagator that gives you a wave function at that point.
Yeah.
And for the inner product, you integrate over all the points on the surface. So that is a codimension one surface. Here this RB infinity is playing that codimension one surface.
The thing I don't understand with the inner product is the inner product requires something on one side and something on the other. Both seem to be coming from inside here.
Yes, the time slice is weird, I agree, yes. I don't know.
You normally cut it like this and then here.
Right. That's the
nothing of
Euclidean.
that.
That's like the Euclidean picture of the inner product. Yeah.
But maybe the fact that this analytic continuation.
Yeah, there's some. Yeah, that's right. So
Yeah.
one piece here is coming from a Euclidean source, the other is coming from a Lorentzian source.
That's
It's a little
partly
bit.
because one of the tau is Euclidean and S is Lorentzian.
Yeah,
right, in
yeah.
your argument.
Yeah.
But why that Lorentzian picked out retarded and all, there's some subtlety here.
That's right. So the,
And in this inner product interpretation, Z is the time, right? So
Yeah.
that doesn't seem to matter very much.
Right.
Anyway, the whole thing's confusing.
Okay.
But I like the way you say it. I mean, if it's just a boundary term, and you're evaluating the boundary term using
Yeah.
these functions,
Yeah,
that's
yeah,
good, right?
yeah. It happens to be this combination of things.
Right.
Right.
So one of them is del phi.
Right.
Del phi caused by the other entity.
Yeah.
Yeah.
Fine.
Fine.
Okay.
Second way relies on special facts.
Special facts. Yeah, but it may be exactly the special fact that it is a two-point function. Those two-point functions, by equation of motion, can always be made a boundary.
Yeah,
Yes.
it's just
Right.
phi
Quadratic
pi.
terms can always be made a
It's always phi pi at the bottom.
Right. because-
yeah, that's effectively what I used in
Yeah.
this calculation.
And the higher point functions have bulk.
And more structure.
So maybe it's,
Yeah, so I guess you could say that we are lucky that we are looking at some quantity in the field theory which only relies on the two-point function around the vacuum.
When you go to higher order.
Then you're going to encounter more pain, basically.
And the way Sandeep says it, it's just basically like the thing that you get there was the symplectic potential.
Yes.
And therefore it's not very surprising that you get the symplectic omega.
Yes, that's where omega comes in at the
Yeah.
end of the day.
So it sounds very reasonable.
Okay, so I guess the only thing I have to convince you now is that this expression actually does match on to this gravity expression. I mean, I guess omega is clear where omega enters the game, but the details. Okay, so then basically the point is you have to do this S integral.
And sorry, it'll match to the gravity for the stress tensor.
Yeah, that's right. So far I'm just working with scalar operators. I'll derive an expression which looks like this, and then the same argument goes through in gravity. There's one subtlety which actually is very important, and I'll tell you what that subtlety is.
Okay, it matches even for scale.
Yes.
You just replace omega with the symplectic form.
The same story for gravity would be that it's h mu nu pi mu nu.
Yeah,
at the
that's right.
boundary.
That's right.
And h mu nu pi mu nu is what is used.
Yep. Okay, good. So let's do this S integral. So the way to do the S integral is the following. So what's this retarded propagator? The retarded propagator is basically some step function, and it's the difference of the two Whiteman propagators. I'm not writing the entries; they're the same entries as this thing. Okay. The retarded propagator is a step function times this combination. You can think of this combination as the commutator, if you like. Okay. All right. So now I can get rid of the step function. So let's say the bulk point is somewhere here. Remember, the bulk point is on this surface, which has gone off to the horizon of the black hole. Okay, this is my bulk point. Now, the retarded propagator is only non-vanishing when this little s, which is the boundary boost time, is to the causal past of this bulk point. Okay, so let me draw a light cone here. And I'm going to call this, sorry for introducing more notation, but I'm going to call these points S star of minus and S star of plus. These are boundary points, and what these are is that it's this bulk point. You send out light cones, and that's where.
And one last, sorry,
Yeah, yeah,
quick
yeah,
question,
yeah,
which
yeah.
is normally when you do when you do Euclidean things,
Yes.
you get time order
Yep.
propagators when you go to line scale. Why do it retarded?
Yeah, good. So that's a good question. I don't know why, but
Algebra.
this is algebra. I mean, at the level of algebra, I couldn't have put a Euclidean propagator here because that would have given me 0. The symplectic form is antisymmetric in the two combinations. So I had to pick something else.
Right.
And the retarder is the thing that worked.
But it seems you only need the fact that maybe up to sign, but that the retarded propagator, the source part is a Dirac function.
Yes.
So that's also true for like the advanced propagator.
Sure. I think you can run with this argument for the advanced propagator as well. Yeah.
But you're saying it won't work for time order.
That's right. That's what I was saying. Yeah. Okay. Good. So this is okay. What I drew here was I drew the sort of light cone. Okay. And so now I can get rid of the step function, provided I basically just do the integral from minus infinity to S star of plus, S star of minus. Okay. As long as this boundary point is the past of SB. Okay. So the same thing. Sorry. So now the S integral is from minus infinity to S star of minus. But actually, if you think about it, I can also go to S star of plus. Okay. The reason I can go to S star of plus is because in this region where these 2 points are space-like separated, the retarded propagator vanishes. The commutator is 0. Okay. So either I can go to S star of minus or S star of plus.
Sorry, maybe I lost track.
Yeah.
What happened to tau?
What happened? Tau is just sitting in this other guy. So you see there are 2 entries in this symplectic flux.
Yeah.
All the S dependence, the
Yeah.
little s dependence is in this guy. And what I'm doing right now is I'm doing the S integral.
Okay.
Yeah. So I'm not sort of worrying about this object.
Because I'm a bit confused, like Advait was saying, that in the same diagram you are going to represent eventually tau as well. And
Not in this diagram, right? This is a completely real-time vector.
Yeah,
Tau is in
but,
the Euclidean time direction.
Okay, I see.
Yeah.
So are you going to think of tau as like a continuation back from Lorentzian to okay, so there's
Tau-
a representation of tau in this.
No, there is no
right?
tau in this integral or in this picture here. That's setting off in the Euclidean time direction, and that's somehow you should think of tau as like creating the sources
So
for the bulk.
you're not really thinking of S as an analytic continuation of some other tau in this game, right? You have a real you
Yeah.
have actually a representation
Yep.
of S.
Yes, that's right. That's right. That's right. And okay, so now I'm going to do this integral by pictures. So it's the best way to do an integral. Good. So what this integral is, you can forget about the step function now. So in the complex S plane, you can do this. By the way, you should tell me when I have to stop.
Well, today's Rajiv's farewell lunch, right?
Yes.
Maybe 1:15.
Okay.
Or
Okay.
In fact, our visitors are invited to the faculty lunch.
Okay. 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 So in 5 minutes, I'll just do this integral and I'll stop. Right. So the argument is pretty simple. You look at this integral.
Rajiv's farewell lunch has happened last Wednesday.
Anyway, the visitors are invited to the faculty.
And
That's faculty lunch.
is there somebody else's farewell lunch?
Oh yeah, I was there. So that was a department thing.
That was a fair, that was not lunch.
I think the lunch is today.
Actually, there was this discussion last Wednesday, and I think
I
you said
see.
that it's today, not last.
That was
attended the farewell faculty lecture.
No, no, you are absolutely right. I was confused.
Okay, so like a 5-minute way of doing this integral is that what you note is, so this is, I'm drawing the complex S-plane here. Okay, in the complex S-plane, first of all, you note that there are these poles coming from the sinh function. These are double poles. Okay, and then there are branch cuts coming from this retarded, these two guys here, k plus and k minus. Okay, they have branch cuts which I've drawn here. Okay, and then this particular combination k plus minus k minus, you can sort of think of that as an integral over Euclidean ke, the Euclidean propagator, but with the following contour. Okay, so if I had a different color chalk, I would draw it in that, but it's this, it's dark, it's the dark lines here. That's the contour of integration. Okay. Yeah, one of them is k plus, the other is k minus. That's the way to think about it. Okay, and the directions are like that. All right, so so this point here is actually S star of minus, and the other point is S star of plus. And from what I told you, the retarded so there is no branch cut in this region, which is the statement that the retarded propagator vanishes in this region. So if I wanted, I can always extend this contour all the way up to here. Okay. The other thing you can do is you can use the KMS condition, which is the periodicity of this Euclidean propagator, to replace this k minus contour, which is just below the branch cut, with a contour up here. This is just a 2 pi shift. Okay. All right. So now we are almost done. Okay. So what happens is the following fact. I'm not going to prove this fact for lack of time, but the following fact happens. When the bulk point approaches the past horizon, you can check that the vertical contour here vanishes. Okay. This one. So the only difference, so this contour is not connected, but I can connect it by putting in a sort of Euclidean line here. When the bulk point approaches the past horizon, it turns out that this guy vanishes, but there are no so there are no poles inside this region of the integral, so the integral vanishes. Okay. So when the bulk point is out here, the integral is 0. When the bulk point goes up on the future horizon, actually this integral, this vertical integral is not 0. But this one is. Okay, so I can extend my contour for free, and actually this is just going to go above here like that, and up here this piece is 0, so I can add it for free. Okay, and then the only contribution you pick up is this double pole which is sitting inside your contour. The double pole gives you a derivative, and so all that does is, so now you've done the S integral. And what you've done is you've basically replaced this object with a derivative of the Euclidean propagator, which is the same thing as the Lie derivative of psi b acting on the Euclidean propagator in the box.
This contour is just below the pole, right?
No, it's
KMS, allowed you to shift it from just above the line there.
Yeah.
So it's just below the.
No, but this pole was, if you
it's
keep
shifted
track
down.
of it,
I see.
yeah, I haven't drawn it very well. These
Yeah,
poles are
I
sort of
see,
shifted
I see.
down.
Yeah.
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 Sorry, I missed just the last. So I can shift the contour up there.
Yeah.
Then what happens? Then you get the.
Right. So what you do is, depending on where the bulk point is going, if it's going to the past horizon, you find that this vertical piece is 0. So I can just complete this contour over here. And so since there are no poles in this region, the integral vanishes. Okay. If the bulk point is going to the future horizon, then this piece is not 0. So you can't just complete it like that. But what you can do is you can extend this integral all the way up here and then complete it here. It turns out that this piece is 0. But then you pick up this double pole. Okay. So all right. Long story short, what happens is that this second order relative entropy then becomes, so now we go back to the sources. There are these integrals over sources. And the 2-point function I just explained to you looks like looks like that. And then you, as I think you were asking about the sources, at this point you can sort of for free glom these sources onto these propagators, and you get omega, delta 1 phi, delta 2 phi, or yeah, I guess delta 1 phi times the lead derivative of delta phi. And this thing is integrated on the future horizon in the bulk. Okay, it's integrated over here. So the last step is that now you can push this symplectic flux from the future horizon to the constant, the t equals 0 slice for free, because none of these propagators have any sources on this real-time section. They're all sourced in the Euclidean plane. Okay. So basically, so this integral, I can as well replace this with the bulk entanglement wedge. Okay. Right. So that's the scalar calculation. The same thing. Yeah.
Your integral was along that slice at some point, right?
Yeah, this one, h plus, right?
And then how did you move down?
So again, the symplectic flux is conserved, so I can push it down.
The boundary?
Right, so there are no boundary terms because both of these objects are sourced in Euclidean time.
Okay.
So they vanish on the real time.
So the A and B labels are basically not there.
Now I've done the I've done these A and B integrals by simply glomming these sources onto these bulk propagators. So they give me the bulk fields.
What were the A and B? I think, did you write lambda?
Yeah.
Sorry, what were the A and B labels?
Those were the locations. So those were basically the locations of these sources. Those are being integrated over.
So it's the same function, lambda of xa.
Yeah, is the source. Yeah.
Okay. So and now this last expression.
Yeah.
Is according to some phi, which is.
Yeah. So this phi is just the ddx lambda of x Euclidean propagator.
And you get Euclidean propagator even though at intermediate steps here you had this.
Right. So here this was Euclidean.
Yes.
This was retarded. But when you remember when I did the S integral, I had these Weitmans, and then I did this contour argument. That's what gave me the Euclidean.
That was what was really worrying me.
Oh.
Because at the strict stage there was this retarded,
Right.
but the field corresponding to the guy
Is the that's
is
right.
the Euclidean.
That's right.
And
that's exactly what happens. You
Yeah.
get the Euclidean.
Sorry, what did you? Sorry, what's the last thing?
see, he's doing some field theory manipulation and then relating it to what's happening to the fields corresponding to that state in the
Right.
bulk.
Right.
So in his original manipulation stage, he had this retarded propagator. And what was worrying me was that when you convoluted that retarded propagator against the source, you would not get the field corresponding.
That's right. That's right.
It's the Euclidean propagator that does that.
Yeah.
Or the time order, whatever.
That's right.
Yeah.
Euclidean.
So even though in this algebraic step the retarded propagator appeared, using the fact that k plus that retarded and Lorentzian are
Yeah.
I see.
very tightly related and
Right.
all this contour business, in the end the final answer is just in terms of Euclid.
That's right. That's right. That's right. So it's indeed the bulk field.
Operators. And the retarded one also came along with an integral over on the real time.
Yes. And so when you do that S integral, that sort of converts you back from the retarded guy to the Euclidean propagator. Yeah. So somehow the S integral, which is somehow crucial which came from BCH and this relative entropy and so on, that sort of saves the day.
So
And
this
it,
contour shift is the thing that's changing from retarded.
yeah.
And then
That's
you
right.
pick up the whole.
That's right.
the
That's right.
residue.
That's right. That's right. Yeah, that's right. Okay, good. So I think I'm out of time. There is one subtlety with this calculation in gravity, but maybe I can. I mean, if you have time, I can mention it. But otherwise, okay. The subtlety is the following. So this expression in gravity, you remember that the similar expression was present in the gravitational ward identity. Okay, that expression is. So that gravitational ward identity is only true in a particular gauge. Okay, so that is written in a particular gauge called the Hollands-Wall gauge, where you fix. So the gauge choice is that you fix the location of the bulk RT surface. Okay, even with the deformation included, the bulk RT surface is fixed, that picks out a particular class of gauges, which is called the Hollands-Wall gauge. And the identity is true in that gauge. Okay? But this calculation that we just did is not done in that gauge, because we used the analyticity properties of these propagators. Okay? These analyticity properties are only true in a particular gauge called the D-Donder gauge, which is not the same as the other gauge. Okay? So then, when you change gauge, what happens in that identity is you get extra boundary terms. Okay? You get new terms on the RT surface. So then you'll ask me, oh, then what happened to those boundary terms in my calculation? I should have gotten more boundary terms. It turns out that if you do this calculation in the graviton case with care, this vertical contour, which did not contribute in the scalar case, is not 0. Okay? It gives a contribution. This vertical contour you can think of as sort of a sort of contribution coming from a tube around the RT surface. Okay? That's why it's a boundary term. And if you compute that, you get exactly the right boundary terms, which match on to the boundary terms you would have gotten from the bulk. Okay, so you can think of this piece here as, if you like, restoring diff invariance in the bulk. Okay, without this piece, the bulk result would not be diff invariant, but this piece comes in, this contribution from the RT surface comes in, and it restores diff invariance. Okay, so in the end, the two expressions match perfectly. That's the only subtlety I wanted to mention. But
What about the C equal to A constraint?
oh yes, so that comes in because you see the thing that I used is the fact that this 2-point function is this bulk expression. Imagine that this is the stress tensor. Then this is, in the CFT, this would have been proportional to CT times some geometric structure. Okay, but this bulk expression is going to give you some other coefficient times the same geometric structure. Okay, so actually I lied a little bit. If you do this gravity calculation in the case of the stress tensors, then there's a coefficient sitting out front. Okay, that coefficient is precisely this CT over A star. Okay, so if you want this to be 1, then you have to sort of put in by hand that CT equals A star. Now, as I think Sandeep and Shiraz were pointing out yesterday, maybe if you use the RT formula, you can also just prove this statement that CT equals A star, but we haven't done that. We sort of just said that we are going to assume that this is true, and then this expression matches perfectly.
This is a normalization factor, first of all.
Yeah.
And the statement that you can, without this factor, you can write this if you have normalized states.
Yeah.
The fact with stress tensor is that the 2-point function has a normalization which is CT.
Yeah.
And this is the only reason CT is appearing probably.
That's right. Yeah, I'm just saying this in the context of the stress tensor.
So for the normalization. Oh, sorry.
You know, I have the following problem.
How did you get A? Oh, sorry, I'm sorry. Why did A at all appear in this?
Which one? This one?
Yes.
So this A star appears because so this A star is the
anomaly, the one.
yeah.
Okay.
Yeah. So it's the coefficient of the universal log contribution in the entanglement entropy.
Yes.
Right, so you assume that you have some bulk ADS spacetime. It computes the entropies of ball-shaped regions in the vacuum. The vacuum entanglement entropy of ball-shaped region C is A star, or A, whatever you want to call it.
But this is a 2-point function calculation. The one
Right. So first you implement the fact that this bulk ADS geometry is computing the entanglement entropy of ball-shaped regions in the vacuum. Okay, that fixes for you the sort of bulk metric. And the bulk, sorry, not the metric, but the the ratio of L to the sum power over G Newton. Okay, that's why it sees A star basically. A star is the contribution of the universal piece in the entanglement entropy. Requiring the 0th order match, if you like, already fixes this ratio, fixes G Newton in the bulk. And then when you do the 2-point function calculation, you have no more freedom left. Okay, it's going to give you the same ratio. Okay, so that's why you get this ratio up front. Does that make sense? Okay.
You know, I have this following problem with
Yeah.
higher derivative actions, that the Hamilton-Jacobi, you know, you could say that H mu nu pi mu nu,
Yeah.
this kind of structure has to come in your calculation of the on-shell action.
Right.
Just from Hamilton-Jacobi.
Yeah.
Because when you differentiate with respect to the
I agree,
boundary
I
phi, you get
Oh, in
priming structure
in higher
in
derivative.
high derivative gravities, because the auxiliary fields come in and their momenta come in, etc.
I see.
And it's not immediately clear
I see.
that when you have taken care of all that stuff, that it's still h mu nu by mu.
I see.
So then, so if you do have essential high derivative
Yes.
terms,
Yes.
then it's not clear that your
Mm,
symplectic form
mm.
would be so simple.
Yeah, yeah, yeah. So good. So I was using this for Einstein gravity. In the higher derivative case, if you make the assumption that the symplectic structure at the boundary has the same nice h times pi kind of structure.
But I wouldn't have it usually,
Ah.
because I have higher and higher or radial time derivatives and so on.
Right.
Then I have to keep introducing auxiliary fields
Right.
to make the thing into many second order
Right.
actions.
Mm-hmm.
And then my symplectic form will have the kind of phi pi of each one of these guys.
Mm-hmm. Yeah, that's.
I have no idea what
Wald deals with this.
Wald deals with that. But,
Because he
but you're saying that this is true for Wald as well.
Yeah.
Ah, okay, I see.
I mean,
What? Yeah.
Typically,
So-
in the case of if we do the same type of thing for null,
Yes.
typically what happens is when you add high derivative terms, because of these extra derivatives, they
Ah.
just fall off. So
Mm.
the symplectic form near the boundary remains unaffected. Because of the extra R
Oh.
derivatives, none of them contribute.
I see.
I see.
So what?
I
Yeah.
don't know if that's the same.
Yeah.
I would expect something similar.
One thing I can say is that if so, we assume that the symplectic structure is of the form delta H delta pi. If you make that assumption, then all of this should just carry over in that
Just one
in that
question.
case.
Say I do not keep this CYA ratio as CYA.
Yeah.
And then you get whatever answer for the bulk geometry you get. So using this bulk geometry, if you calculate suitable, let's say 3-point function or 4-point function of stress tensors,
Yeah.
then it should also consistently get the same factor of CRA.
Yeah, that's a good
That
question.
gives a constraint, and that probably will determine this.
Yeah, that's a good question. We haven't really tried the higher
But
point
this
calculations.
could, in principle,
Yeah, that's quite
gives
possible.
a equation.
Absolutely, yeah. It's quite possible that if you go to next order, that RT formula just fixes for you C over A. That's quite possible. We haven't done that.
So just continuing, the way Wald, probably before it, but they define the symplectic structure is just this. They vary the action.
Yes.
And then they get E plus d theta. D theta is some one-formal phase space because it's evaluated on your variation. Then they take a d of that on phase space, and that gives them the symplectic structure. And that way of thinking is not restricted to any particular number of derivatives.
And also it does not get contributions from boundary, from total derivatives, or from any boundary term. Because
Yes, it does not
because
get.
because that
It
will
will be d of d.
D will be d of d. So
Yes.
even if you add high derivative terms, then you have to add extra boundary terms, to make it quadratic. Whatever boundary terms you add, they won't contribute to the symplectic form. So there's only various bulk terms which have extra derivatives. And then when you then try to push the symplectic form to an asymptotic region, most of the high derivative contributions just die.
It's an interesting.
Well, I'm surprised. This seems to be like a miracle, except for this infinity thing. Because if I take a particle with x, 4 dots equal to something, okay, so 4 time derivative thing, I know that the phase space is 4-dimensional, right? It's not a 2-dimensional.
Right.
So therefore, clearly it has this other guys.
No, but let's do the way Wald do it.
Yeah.
So what he will get is dx wedge dx triple dot as his symplectic form, because it's just the path that's total derivative.
Okay.
Okay.
Fine.
Now that will be his symplectic form, and now you can evaluate that symplectic form on all of phase space.
I can do that, but this phase space will not space of solutions. My
No.
space of solutions is 4-dimensional.
No, no. So there's a form,
Mm.
which is just some form, and now you evaluate it on solution space.
Oh, so you're saying let it be a 4-dimensional space, but I have a two form like
This is a two form.
like this.
On any given two solutions, evaluate dx, wedge, dx to present. So it's a 4-dimensional phase space, as you said.
Mm.
And
But there is
on-
another term which is not coming into place, which is dx dot wedge dx double dot. That is also there, I know. Using the
maybe I said it wrong. So your Lagrangian was x.
x double dot square, I believe.
X double dot
X
square.
double dot square.
So we have to take the variation and take the total derivative of that. So whatever that was
Hmm.
will be your symplectic, will be your theta, and take b of that, and that will be omega. Now that gives you some form. It's independent of the question of what your dimensionality of phase space is.
Yeah, that gives me some form, and that's enough for some purpose.
It was enough for what Wald wanted.
What world?
Yes. So I mean, it's a natural definition of symplectic form, but it's an interesting question whether you can quantize this. These kind of phase spaces with this kind of symplectic form. Something should go wrong with unitary.
Something should go wrong.
Yeah.
Because it can clearly go into the degrees of freedom, can go into those other things which have been ignored here.
For instance, we know that in field theory, high derivative Lagrangians are impermissible, right?
Huh?
Impermissible because they always come with ghosts.
Yeah,
And anything that comes in quadratic order with high derivatives will always lead to ghosts. We know that.
So is it going to be non-degenerate on the whole space of solutions? Classical solutions?
Yeah, that was not important for world.
That is certainly important here. You have
It's to quantize. Yeah, that would be important to change. I'm not sure. Now maybe that is the problem. Maybe it's degeneracy, or maybe something worse because, or maybe some non-positivity or something. That the Hamiltonian. I mean, the thing that you would see if you had high derivatives typically is propagators with the wrong sign, which is like you're creating states with negative norm. So maybe the compatibility of positivity of symplectic form and Hamiltonian or something like that. Yeah.
possibility of symplectic form.
No, what I mean is positivity of the Hamiltonian when quantized with respect to the symplectic form. So there's some relative positivity that's important. As an operator, it should be positive. I think it would be interesting. I mean, is it ever possible to make sense of high derivative theories, the quantum mechanics? I mean, just at the classical level, one very effectively uses it. So one shouldn't discard. I mean, one shouldn't be too skeptical. I think, but something should go wrong here. I'm sorry.
Yeah.
for this.
No,
Your thing is not p squared.
What?
Wait, your stuff. So you are saying x triple dot is the canonical conjugate to
I
x.
may have said that wrong. It's whatever the total derivative you get on variation. So if you had x double dot times x double dot, you'll get one term which is x dot
X double dot.
times delta x double dot, and then no, you have to do two integration by parts, so it'll be more complicated. Because then what you want to do is make the whole thing proportional to delta x
Yeah.
times something. So you'll have two terms in the symplectic form. One term which will have delta x dot, and one.
So this procedure is done by whoever, Ostrogradski or something.
Okay.
And they get the what I would call the correct symplectic form, which will have x triple dot of the kind that you were saying, and then the other guys also. You
Yes.
see, there are three momenta here,
Yeah.
which is x dot, x double dot, and x triple dot.
Huh.
Okay. And they all come.
Huh.
Yes.
Huh. So exactly. So this procedure would give that to you. So presumably then it will be non-degenerate from Gotham's point of view because they all appear in. But I think there should still be some trouble. Right? I mean, if you try to quantize them.
Yeah. I see. I was worried by just the first thing, that it's not looking like dx wedge dx dot.
I just said it wrong. I think. Yeah, it's something.
Yeah.
In gauge theories, unless you fix all the gauges, you will get this to be degenerate. So in some sense, if you fix all the gauges, then the degeneracy is gone away. But still, you are saying there could be more things which can go wrong, obviously.
I mean, you get some Poisson brackets by doing this procedure, but I guess the question is, can you realize this as in the usual sense as an operator algebra on a Hilbert space?
With positivity.
With positive norm?
Yeah.
Is that, I don't know whether Ross
I think we should be skeptical, because you see, suppose we take a propagator, which is like del to the 4. We know at large momentum it scales like 1 over k to the 4, which is inconsistent with the Lehmann representation theorem and unitarity. We just know that. So, for instance, if you do a field theory, yeah. So I think we should expect that it's not unitary somehow. If we take something like Gautam's example, and it would be interesting to ask if it's ever possible to make it unitary. You know, this is the issue of, must be tightly related to the fact that Gauss-Born is ruled out as an allowed theory. Right? It's not somehow, not okay. It looks classically okay, but it's not okay. I mean, somehow there should be the only allowed ways of adding higher derivatives should be by integrating out good stuff in the union, not by doing junk. And even though Waldo's able to make sense of it, it shouldn't really be.
Yeah, like Nima's paper.